Welcome back to the Deep Dive. Today we're tackling something that demands, well, extreme precision. Ocular biometry. We're talking about measuring the inside of the eyeball, things like its exact length or the curve of the cornea.
Yeah, and these numbers, they sound technical, but they're absolutely fundamental for some major medical decisions.
Right. They're not just for, research papers, they're critical.
They really are. Think about cataract surgery. Getting that intraocular lens, the IOL, powered just right, depends entirely on these measurements.
And it's not just older patients, is it? There's a huge issue with myopia, nearsightedness, especially in kids.
Exactly. A massive global issue. And tracking how that myopia is progressing, managing it, it all comes back to getting precise, repeatable measurements over time.
So, okay, a new gadget comes along, a new measurement device. It can't just, show up and expect to be used.
Absolutely not. It needs to be put through its paces. Rigorously tested against whatever we currently trust as the gold standard.
And that's our focus for this deep dive. We're looking at a study that did exactly that. It tested a new contender, the MYAH US from Topcon.
Right, the MYAH. It's quite versatile, uses a technology called optical low coherence interferometry. Fancy name, but basically a way of using light waves to measure.
And it was compared against the current heavyweight champ, the Lenstar LS900 from Hog Street.
Lenstar. Also uses light, but a slightly different technique, optical low coherence reflectometry.
So the study zeroed in on healthy young adults and asked two key questions about this new MYAH device.
Yeah. First, intercession repeatability. If a patient comes back a few days later, does the machine give you the same reading? Is it consistent over time?
And second,
Agreement. How well do the MYAH's numbers actually match up with the established Lenstar measurements?
okay, let's get into the details. Let's unpack this measurement showdown.
That sounds good.
So before we dive into the results, maybe we should quickly recap why these specific measurements are so important. You mentioned a few.
Definitely. Let's start with axial length, or AL. That's just the length of the eye, front to back.
Okay.
For myopia management, that's like the number one thing, is the eye getting longer. That's how we know if treatments are working or if the myopia is progressing.
Makes sense. What else?
Then you've got corneal power, CP, basically how much the cornea bends light, and white to white distance, WTW.
White to white, that's the width of the colored part, the iris.
Essentially, yeah.
Yeah.
The visible diameter. And those two, CP and WTW, are critical if you're fitting specialized contact lenses, things like orthoc or scleral lenses.
Ah, okay. Get those wrong and the lens just won't work properly.
Exactly. Bad fit, bad vision. And all four of these, AL, CP, WTW, and pupil diameter 2, are vital for those IOL calculations in cataract surgery we mentioned earlier.
Got it. So high stakes all around. How did they actually run the study?
It was pretty well designed. They took 40 healthy young adults, average age around 25.
Great.
Each person came in for 2 separate visits, about 2 to 4 days apart.
And the controlled for time of day, I saw?
Yeah. They did, yeah. Both visits were scheduled within the same 1-hour window for each person. That minimizes any diurnal variation, tiny natural changes in the eye during the day.
Smart. Okay, and back to the tech difference for a second. MYAH uses interferometry.
Right. It looks at the frequencies and the interference pattern of light waves.
And Lenstar uses reflectometry.
Yeah, that one measures the time it takes for a light signal to bounce back.
So different methods. Almost like using two different kinds of rulers, in a way.
Kind of, yeah. One uses frequency, one uses time delay, both super precise, but because the physics are different, you can't just assume they'll give the exact same answer. You have to prove it.
Which brings us to the results. First up, repeatability. How consistent was the MYH device over those 2 separate visits? Why look at across visits rather than just taking a bunch of ratings in one go?
Good question. Intercession repeatability, that's consistency across different visits, is way more relevant to actual clinical practice.
How so?
Well, think about it. When a patient comes back, things aren't identical. Maybe they don't put their chin in the exact same spot on the rest.
Right.
Maybe the room lights are a bit different, or their tear film is less stable that day. Real-world stuff. A device needs to be reliable despite those small variations. Intrasession within one visit doesn't capture that as well.
Okay, that makes sense. So how did the MYAH do on this real-world test for the big parameters like axial length?
It did really well. Very high intercession repeatability for axial length, corneal power, and white-to-white distance.
Meaning the numbers from visit 1 and visit 2 were pretty much the same.
Statistically, yes. There was no significant difference found between the 2 visits for those key parameters.
I see some stats here. ICC for axial length greater than 0.99. What does that actually mean for, say, a doctor tracking a kid's eye growth.
Yeah, an ICC that high, close to 1.0, basically means you can trust the machine. It tells you that almost all the variation you see in measurements comes from real differences between people, not from inconsistency in the device between sessions.
So if you measure a kid today, and then again 3 days later, and you see a change.
You can be very confident it's a real biological change, not just the machine having an off day.
That's huge. And the limits of agreement for AL.
Wow.
Wow. NIGO 0.04 to plus BISO 0.04 millimeters. That sounds incredibly tight.
It is extremely tight. And interestingly, the study found the actual repeatability, plus or minus 0.02 millimeters, was even better than what the manufacturer, Topcon, specifies for the device.
Better than advertised. You don't see that every day.
No, you don't. It's a strong result. But there's always a but in research, isn't there?
Uh-oh. Which
Yeah.
measurement caused trouble?
Pupil diameter, or PD. That was the outlier.
The pupil anomaly. What happened there?
It was just much more variable across visits.
Yeah.
And interestingly, for both the MYAH and the Lenstar,
Both devices struggled with consistent pupil size.
yeah, the coefficient of variation for MYAH was around 7%, which sounds small, but compare that to the 0.06% for axial length. It's way higher variability.
So what's going on? Is it the machines or something else?
Well, what's fascinating here is the researchers think it's likely not the instruments, it's the pupil itself.
Ah, because pupil size changes all the time.
Exactly. It's dynamic. Tiny changes in light, maybe even the patient feeling a bit anxious or relaxed. That can cause a real physical change in the pupil size between visits. No instrument can control for that perfectly. It's biological noise, not instrument error.
Okay, that makes sense. So test 1, repeatability. MYAH passes with flying colors except for the inherently variable pupil.
Pretty much, yeah.
Now for the big one, test 2, agreement. How does the MYAH stack up against the gold standard, the Lenstar? Did they give the same answers?
The overall story here was also very positive. They found good agreement between the two devices for the main parameters: axial length, corneal power, and white to white.
Let's drill down on axial length again since it's so critical for myopia. How close were the MYAH and Lenstar readings?
Extremely close. The average difference was just minus 0.01 millimeters. Tiny.
Minus 0.01.
Yeah.
So the MYAH measured slightly shorter on average.
Yes, but only by 1/100th of a millimeter. And the 95% limits of agreement were also very narrow, from mere 0.07 to plus 0.04 millimeters. That indicates really good agreement overall.
Okay, hold on. I see in the notes here that tiny 0.01 millimeter difference.
Mm-hmm.
It was actually statistically significant. The p-value was 0.004.
Ah, yes. Good catch.
So even though it's minuscule, the stats say it's a real difference. Wouldn't that worry someone doing, say, a critical IOL calculation? Isn't any statistical difference a red flag?
That's a really important point. It highlights the classic difference between statistical significance and clinical significance.
Okay.
Because the study had a decent number of participants, and the measurements from both devices were incredibly precise and consistent in these healthy eyes. Their statistical analysis was powerful enough to detect that minuscule systematic difference of 1/100th of a millimeter. The math says it's real, but clinically, for a doctor making a decision, a difference that's small, literally less than the width of a tiny dust speck, it just doesn't matter. It has no practical impact on the outcome.
So it's like measurable noise,
Yeah.
but not enough to change what you'd actually do.
Exactly. It's statistically real but clinically irrelevant noise in this context. And actually, when you look at other studies comparing different devices to the Lenstar,
Yeah.
they often found differences around 0.04 millimeters, so 4 times larger than what they found here between MYAH and Lenstar. This Angnischer 0.01 millimeter difference looks even better by comparison.
Okay, that perspective helps. So AL agreement is excellent, clinically speaking. What about corneal power?
Good agreement there, too. No significant difference found between the devices for CP.
Great. And the other two, white to white and the troublesome pupil diameter.
Ah, yes. For those two, WTW and PD, there were small but statistically significant differences.
How small?
For WTW, the mean difference was manacle 0.13 millimeters. For PD, it was a bit larger, 0.27 millimeters on average.
Okay. And did the study offer any ideas why, especially for the pupil difference? I remember reading something about the right eye versus the left eye with the Lenstar.
Yes, they had an interesting hypothesis about the Lenstar's procedure. It seems the Lenstar tended to measure the right pupil as being slightly larger than the left pupil.
Why would that happen?
They think it might be the light the Lenstar projects during the white-to-white measurement. When it measures the first eye, usually the right, That light might actually cause the pupil in the other eye, the left one, to constrict just a tiny bit before it gets measured.
Whoa, so the act of measuring one eye affects the measurement of the second eye.
Potentially, yeah. It's an artifact of the specific measurement sequence and lighting.
Did the MYAH show that same pattern?
Not really. The MYAH measured the left pupil as slightly larger than the right, but the difference was much smaller and well within the normal range of what's called physiological anisocoria.
Which is just a normal slight difference in pupil size between a person's two eyes.
Exactly. Nothing unusual there.
Okay, so stepping back from all the individual numbers, if you're a clinician looking at this study, what's the main takeaway message about using the MYAH?
The bottom line is pretty clear. Yes, there are some tiny statistically detectable differences, especially for WTW and PD. But for the most critical parameters, axial length and corneal power, the agreement is excellent, and any differences are almost certainly clinically insignificant.
Meaning, you can trust the MYAH.
Meaning the evidence strongly supports using the MYA and the Lenstar pretty much interchangeably for these key measurements, especially for things like IOL calculations and, crucially, for tracking myopia progression, where that AL measurement is king.
So what does this all mean going forward? What's the impact?
Well, it strongly validates the MYAH for use in this population, healthy young adults. It shows it's consistent with itself over time, and its results line up very well with the established gold standard.
Which is good news for one.
It's great news for applications like myopia management, particularly globally, where you need efficient, reliable devices to track axial length changes in potentially millions of kids. This study gives clinicians confidence in adopting the MYAH for that purpose.
But, like all studies, this one had its limits, right? The researchers pointed one out specifically.
They did, and it's important. This validation was only done in young adults with healthy eyes, clear ocular media, no cataracts, no corneal scars.
Right. Crystal clear views for the instrument.
Exactly. And remember that fundamental difference in technology, interferometry for MYAH, reflectometry for Lenstar,
Yeah.
frequency versus time delay.
So here's the final thought to maybe chew on. If these two fundamentally different ways of measuring light gave such similar results in these perfect, easy-to-measure eyes, what happens when the view isn't so clear? Imagine trying to measure through a dense cataract or a hazy cornea. Could it be that one technology, maybe the frequency analysis, maybe the time delay, actually performs better than the other when things get optically challenging?
So in tougher clinical cases, that small tech difference might suddenly become a big difference in performance. It's possible. We don't know yet. That's precisely what the researchers suggested needs to be investigated next, testing these devices head-to-head in patients with cataracts or other media opacities. Will one prove superior when the going gets tough?
A really critical question for future work.
Definitely.
Well, this has been fascinating. Thanks for diving deep into the world of precision eye measurement with us.
My pleasure.
We'll catch you next time on The Deep Dive.